All right, so for this week, you've had chapters 5 and 6. Those are kind of heavy with math. From here on to the end of the semester, we sort of leave math behind. That's not saying we won't see it anymore. But generally speaking, we're done with the mathy part of things, moving on to the much more conceptual side of chemistry and chemical bonding in particular. Chapters 9 and 10, where we'll finish out the semester, both focus on different types and different theories that surround chemical bonding. This week's material is a little bit light. It's a good foundation for what we'll do next week with Lewis structures, but generally speaking, this week's material is a little bit lighter than it has been the last few weeks. Chapter 9 starts out with sort of an introduction to Lewis structures and different types of bonding. We'll get much deeper into Lewis structures next week, but for this week, let's discuss how we classify bonds and different kinds of bonding and things like that. Here we go. So this is chapter 9, our chemical concepts. All of chemical bonding deals with electrons, and specifically those valence electrons. Electrons that are in the core of an atom don't really do much in terms of bonding, and so we have to pay attention to those valence electrons. If you remember from previously in the semester, we know the number of valence electrons based on the position in the periodic table. This first group has one valence electron. This second group has two valence electrons. We'll skip over the transition metals for now, but this group has 3 electrons all the way over. This group has 8. This group has 7, right? You can fill in the in-between, but based on its position, based on an element's position in the periodic table, we know the number of electrons that they have. For ionic compounds, that ionic bond is formed from the transfer of an electron from one element to another. Once we have those ions formed, then it's the ionic charges. Electrostatic force, right? This is charges. Those charges hold the two ions together. And so a simple example, if we have lithium, on the previous page, hopefully you noticed that they represent electrons with little dots, and so lithium has just one valence electron, so there he is with his dot. If he reacts with a fluorine atom, now notice I'm talking about a single atom of fluorine. I'm not talking about fluorine F2. If lithium reacts with a single fluorine atom, what's going to happen is that we're going to transfer this electron to fluorine. Right? And actually, I will make that electron blue, just so we can kind of keep track of it. In real life, we're not very good at keeping track of electrons, but for the point of this demonstration, we'll do it. So then, we make this compound that's lithium plus and fluorine minus, and again, I'm going to draw in that blue electron. So lithium gave his electron over to fluorine. Fluorine is now F minus instead of regular F without a charge. We can think about this as being sort of a two-step process. Lithium with an electron giving up his electron to become lithium plus. What process was this again? Do you remember? It's from chapter 8. It's been a minute. But we call this the ionization energy, and more specifically the first ionization energy. Now, the fluorine atom, he's got his 7 electrons. He's adding an electron to become F minus, and I'll again draw in all of his electrons here. Atom adding an electron, we call that the electron affinity. And in this example, right, the electron that lithium loses is the electron that fluorine gains. And so we can add these two together. We just learned Hess's law, right? And so if we add these two together, we get lithium with a dot, and fluorine with 7 dots. Now our electrons cancel. We have one as a product and one as a reactant. I'm left with Li plus and F minus. Fill in his electrons, which of course we write as LiF. And so this is sort of the breakdown of how ionic compounds are formed based on the transfer of an electron. It's really the loss of an electron from the metal and the gain of an electron from by the nonmetal. What we call this is the lattice energy. Ionic compounds form crystal lattices where these ions are next to each other, and so that lattice, that crystal lattice, and the energy it takes to form it, or the energy you get out when you form it. And so that lattice energy in our textbook is called U. Is the energy that you have to put into a crystal to completely separate all of those ions into individual pieces. And not just pieces, but gas phase pieces. And so that lattice energy, U, is equal to some factor K times the charge on the positive ion, Q plus, Q for charge, times the charge on the negative ion, so Q plus and Q minus, divided by R. So again, that lattice energy U, Q plus is the charge on the positive ion, Q minus is the charge on the negative ion, and then R is the separation between those two nuclei, between those two ions. Okay. And so if we investigate this a little bit, in order to have a large lattice energy, so in order to have an increase in U, we need to have either large charges, so an increase in charge, or to have an increase in lattice energy, we need to have a decrease in this R value, this distance. Okay. So there's two ways that we can think about having a large lattice energy, either a large charge or a large distance. Now, we have not gotten into the distances between atoms, and we are not going to think about it too much. We're going to mostly focus on the differences in charge. If we go to the next page, we'll have some different compounds and their lattice energies. And so, if we look here, lithium fluoride, that's a +1 and a -1. Right? If we go down here to MgO all the way at the bottom, that's a +2 and a -2. And so at the top, we have Q plus times Q minus, 1 times 1 is 1. At the bottom, Q plus times Q minus 2 times 2 is 4. So the electrostatic potential, that lattice energy, is 4 times greater. Yes, magnesium is a little bit bigger than lithium. Yes, oxygen is a little bit bigger than fluorine. But that distance piece is not as important to us as the charge piece. We'll take a look at that. If we look here, the lattice energy, 3890, so almost 4,000 versus just 1,000. Again, this is a 1 on top, this is a 4 on top. That difference is almost entirely due to the change in charges. If we pick another pair, sodium chloride versus sodium iodide, right? These are both +1, -1. The only difference is that iodide, being 2 periods lower on the periodic table, has a much larger radius, and so therefore the distance between those ions is going to be larger. But you see here, the difference in the lattice energies is not that great. it's 100 out of 800, so about 1/8 as is smaller for the larger ions. And so the difference in radius is not nearly as much of a player as the difference in charge. Okay? All right. So that's ionic bonding. Moving forward to covalent bonding. Now, instead of this transfer of electrons where they're held together by the electrostatic force or that difference in charge, now we have these atoms that are held together by the sharing of atoms that are held together by the sharing of electrons. And so why would atoms choose to share electrons rather than give up electrons? It has to do with something called an octet rule. If you think back to our periodic table, the first group has 1 valence electron, the second group has 2 valence electrons. If we jump all the way across to the noble gases, those noble gases have 8 valence electrons. Their valence shell is full. So this octet rule, tells us that atoms want to have a full shell or subshell. And so that means for most atoms that they need 8 electrons in the valence. Lithium's a little bit different because he only had 3 electrons to begin with. He would rather lose one to become like helium, a noble gas, but helium only has 2 electrons. We call that a duet of electrons. If we looked at sodium instead of lithium, sodium plus becomes like neon. Neon has 8 valence electrons. And so sodium has a happy octet when he loses one instead of gaining 7. Much easier to lose 1 than gain 7. A good example of the octet rule is fluorine being diatomic. If I take 1 fluorine, and then I'm going to switch colors to have another fluorine, when they react, let me draw this fluorine over here, my red fluorine. You can see that here they have a shared pair of electrons. Okay, I'm going to erase this real quick. And actually I'm going to draw some circles. If we look here, around this fluorine we have 8 electrons. You can count those dots, see that there are 8. Around this fluorine we have 8 electrons. Count those dots, see that there are 8. This space in between here is a shared electron. It's an electron from each fluorine atom that's shared with the other atom. And this here is called a bonding pair of electrons. And that's what makes it a covalent bond rather than an ionic bond. Just for the sake of completeness, these are called non-bonding pairs, or we also call those lone pairs, because they're not being shared, they're just with a single atom. Okay. And so we have a bonding pair here, so that gives us a single bond. Now, it's a single bond, but it's 2 electrons. Let's take a look at some more. Let's take a look at water. Water, I'm going to use my colors again. Hydrogen only has 1 valence electron. There's a hydrogen on both sides of oxygen. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. And so if I have a hydrogen, 2 hydrogens and an oxygen, what I end up with is an oxygen here with his 6 electrons, and our hydrogens with their single electron each And for oxygen, his octet is full with 8 electrons, and each hydrogen doesn't have an octet. I mentioned earlier that hydrogen's okay with just 2 electrons. And so hydrogen has a duet, so this is a full duet of electrons, and that's true for both hydrogens. Oxygen has a full octet of electrons. Okay. Both of these, so this area here, as well as this area here, right? These are covalent bonds. And again, those are single bonds. So a single bond is where we share 2 electrons. Okay. Let's look at an example of a double bond. If I have carbon dioxide, carbon has 4 electrons. Oxygen has 6. 2, 3, 4. I'm going to put his other 2 here. You'll see why in a minute. Okay. My color is getting a little bit away from me. If we look here, oxygen has a full octet. This oxygen has a full octet. And carbon now has a full octet. Right? But what is different is that now we are sharing 2 pairs of electrons are being shared. Right? That's true here as well. We have 2 pairs of electrons. 2 pairs of electrons means that we have one double bond. So 2 pairs of shared electrons is the same as 1 double bond, is the same as 4 shared electrons. Okay? In a last example I'll give you, nitrogen. Last example I'll give you is nitrogen. N2 forms a triple bond. Each nitrogen has 5 valence electrons, and so they have to share 3 electrons in order to get a complete octet. But if we look, each of these nitrogens has 8 electrons around it, and now we're sharing 6 electrons, or 3 pairs of shared electrons. That means that we have a triple bond. In every case where we have a pair of electrons being shared, for clarity's sake, we often represent a single pair of shared electrons as one line. And so I'm going to rewrite all of these. Here we have H line, O line, H. And then oxygen still has those lone pairs of electrons, but that shared pair of electrons becomes a bond. Right? We represent a single bond with a single line. Here for CO2, we have 2 pairs of shared electrons on both sides, and then each oxygen has his lone pairs of electrons. And then lastly here for nitrogen, we have a triple bond, and each nitrogen has 1 lone pair of electrons. And so when we count up electrons, right, there's a total of 10 electrons in this nitrogen molecule. We've got a pair of electrons here, that's 2. A pair of electrons here, that's 2. Each line that we draw, each bond that we draw, is 2 electrons. And so this is 6 electrons in this triple bond.